Isomers. Isomers play an important role in organic chemistry, inorganic chemistry, and biology. This video will focus on the constitutional isomers. This chart shows a broad classification of isomers. I'll be focusing on this side, constitutional isomers, and the three subsets, positional, functional group, and skeletal isomers. Isomers are compounds having the same molecular formula but different structures. The word comes from Greek isos, meaning same, and mer, referring to a part, therefore compounds having the same parts. You've seen mer in polymer, which means many parts or many units. Let's start with the molecule C2H6O. This is a molecular formula. It doesn't tell us anything about the structure. If you try to connect atoms so that carbon has its normal 4 bonds, hydrogen its 1 bond, and oxygen its 2 bonds, here is one structure. If we move oxygen in between the 2 carbon atoms, we get this. The first one represents a molecule of ethyl alcohol, also called ethanol. This one is called dimethyl ether, a very different compound from alcohol, both in physical and chemical properties. For example, alcohol is a liquid at room temperature as it boils at 78 degrees Celsius, while dimethyl ether is a gas at room temperature because it boils at minus 24 degrees Celsius. It's interesting and quite amazing how the same atoms can be joined in different ways to produce vastly different chemical and physical properties. Now, before we go on to the types of isomer, I want to explain 3 kinds of formulas. A molecular formula like this shows only the ratio of atoms in the molecule, and so is not very informative. Drawings like these are called structural formulas because every bond is shown, so it shows exactly what the connections are. A third version is in between these. For example, we can write ethyl alcohol like this, or like this, where only the OH bond is shown. This is a more compact way of writing it, and is called a condensed formula. Sometimes all bonds are left out, like this. Here is the same notation for dimethyl ether. I'll be using both structural and condensed formulas in this video. Now, just for the sake of completeness, I will show an even more compact version, the line diagram. Butane looks like this, with 4 carbons and 10 hydrogens. Ethyl alcohol is written like this, and dimethyl ether is written like this. If you are familiar with this system, that's fine, but if you haven't reached this point yet, you can ignore this, as I won't be using it here. Both structural and condensed versions should work for everyone. Because we can sometimes be fooled by the way we write things on paper, we need to be clear when it's not an isomer. It's not an isomer when there is free rotation about the carbon-carbon bond. This doesn't change the compound. You'll know from working with models that it's easy to rotate groups around a single bond, and you haven't really changed the molecule. But it's not so easy to see this on the page. So, for example, if we just write the chain like this, is this one the same or different? They're both the same, as is this one. The CH group, called methyl group, can be moved on paper like this, or this, without altering the original structure, so they're not isomers. Here's another representation. The zigzag pattern actually mimics the true structure of this molecule as shown by X-ray analysis. But again, it's not an isomer. Drawing the straight chains literally straight is done for convenience and clarity. Next to note are that all positions on a single carbon atom are equivalent. For example, let's consider this molecule in which one of the hydrogens has been replaced by a chlorine atom. If we draw it like this, are these the same or different compounds? All the connections are still the same atoms connected to the same atoms, so these are equivalent structures. Similarly, if we show the chlorine in these positions, they also do not change the molecule, so these are not isomers. Now here's a question for you. Are these 2 molecules isomers? If you look at this methyl group here, you can see I can just rotate it down to the bottom, showing that they're the same. So these are not isomers, they're the same compound. Constitutional isomers. These are compounds having the same molecular formula but different constitution or structure. These used to be called structural isomers, but the designation was changed in 1996. Although many textbooks still use the term structural, the proper term is constitutional. Let's look at C4H10. With 4 carbons, this is butane. How do we draw it? The simplest way first is to draw the chain in a linear manner like this. You may see it named as N-butane, where N stands for normal. The word butane alone automatically means the normal straight chain version by itself with no side chains. Here is a condensed formula. Is there another way we can write this structure without making it into a ring? If we take this group and then attach it to this carbon, it would look like this. With methyl group on carbon 2, this makes it 2-methylpropane, a different molecule and therefore an isomer. Here is a condensed version. What if we took this group and attached it to this carbon? Would this be another molecule? We can rotate this methyl group left and this one right, so we end up with a straight chain of 4 carbons the same as the original one. This reasoning shows why there are only 2 isomers of butane. Try this. Draw and name all isomers of C5H12. You should pause here, try this on your own, and then come back and see how you did. The simplest isomer is the straight chain, which is pentane. Here is the condensed version. Let's take this methyl group and move it here. But it's already attached here, right? So that's nonsense. So let's move it to this carbon. This makes a second isomer called 2-methylbutane, condensed version. Now going back to the first one, what if we put this methyl group on this carbon? Would that be another different molecule? That would be methyl on carbon 2 like this, which would still be 2-methylbutane, so not a new isomer. What if we took this methyl group and attached it to the same carbon number 2? This looks like another isomer because the skeletal structure has changed. Here is the structural formula and its name 2,2-dimethylpropane. There are just 3 isomers of pentane. With this process, you can determine the structures and numbers of isomers for larger hydrocarbons. For example, I'll leave it to you to see if you can find the isomers of hexane C6H14 and heptane C7H16. I'll give the answers here, but you can stop the video if you want the challenge of trying it yourself first. Here's the number for hexane, and here it is for heptane. Beyond those, the numbers rise rather quickly. For C10H22, there are 75 isomers. And for C30H62, try making a guess. Nope, too low. The answer is over 4 million. I need to point out now that we have been considering the isomers on this page as constitutional isomers because the atoms were connected differently in each case. But these are also a subset of constitutional isomers called skeletal isomers because the skeletons changed, as we saw, from one molecule to another. There are 2 other subsets as shown in this classification, positional isomers, functional group isomers, and I will deal with them very briefly now. The positional isomer refers to compounds that differ in their positions of double or triple bonds or of a substituent. One simple example here is 1-butene. But1-ene is a more modern name. Both are acceptable. If the double bond changes to carbon 2, we now have an isomer called 2-butene or but2-ene. Now the positional isomer based on substituents. Here is 1-fluoropropane. If the fluorine is in this position, we get a positional isomer called 2-fluoropropane. Functional group isomers involve certain pairs. For example, alcohol and ether. Here is ethyl alcohol, or ethanol, and here is dimethyl ether. These were the examples I started this video with. Alcohol and ether are different functional groups, but since they have the same molecular formula, they are isomers. You can call them constitutional isomers, or be more specific and call them functional group isomers. The second example involves organic acids and esters. Here is acetic acid, also called ethanoic acid, and here is methylformate, also called methylmethanoate. Both have the same molecular formula and so are examples of functional group isomers. The final example is aldehyde and ketone. This is propanol and acetone, or propanone. These functional group isomers have the same molecular formula. Skeletal isomers do not have multiple bonds, substituents, or functional groups. The changes occur in their skeletal structures. The connectivities or bonding connections differ from one isomer to another. Most introductions to isomers begin with the hydrocarbons like these. They may be called structural isomers, but, as mentioned since 1996, are more properly called constitutional isomers, but they can also be called skeletal isomers. And this ends the video on constitutional isomers.